Before showing a matrix that refuses to diagonalize, let us use diagonalization on a matrix that behaves nicely. Naturally, it gives the Fibonacci formula, because the golden ratio keeps showing up like it owns the place. Define the Fibonacci sequence by A1 equals 1, A2 equals 1, and AN equals AN minus 1 plus AN minus 2. For n at least 3. The goal is not just to generate terms, the goal is a closed formula. Because repeatedly adding previous terms is charming until n becomes large and patience becomes extinct. Package 2 consecutive Fibonacci numbers into one column vector. Then the recurrence becomes one matrix multiplication. The top entry adds the previous two terms, the bottom entry just shifts an-1 downward. This is the matrix version of bookkeeping, except actually useful. Let xn be the column vector with entries an and an-1. Then xn equals a times xn-1. So xn equals a to the n minus 2 times x2. The Fibonacci formula is now hiding inside a matrix power. Subtle? No. Effective? Annoyingly, yes. We already computed this characteristic polynomial before. T squared minus t minus 1. Its roots are phi and psi. Because phi and psi are roots, either one satisfies lambda squared equals lambda plus 1. Now test the vector lambda comma 1. Multiplying by a gives lambda plus 1 in the top entry, and lambda in the bottom entry. But lambda plus 1 equals lambda squared. So this is lambda times the original vector. That is the eigenvector check, not a magic coupon. So phi comma 1 and psi comma 1 are eigenvectors. Different eigenvalues give independent eigenvectors. So the matrix is diagonalizable. Put those eigenvectors into the columns of P. Then A equals PDP inverse. This is the diagonalization we wanted. The whole point of diagonalization is that powers of a diagonal matrix are painless. Raise the diagonal entries. That is it. Math briefly stops being hostile. So a to the n minus 2 is p times d to the n minus 2 times p inverse. Now we only need the first coordinate of the resulting vector. The initial vector x2 can be written as a combination of the two eigenvectors. The coefficients are phi over square root 5 and negative psi over square root 5. Applying a to the n minus 2 just multiplies the phi eigenvector part by phi to the n minus 2. And the psi eigenvector part by psi to the n minus 2. Taking the first coordinate gives Binet's formula. An equals phi to the n minus psi to the n. Divided by square root 5. The recurrence became a matrix power. And diagonalization turned that power into powers of eigenvalues. That is why eigenvectors are not decorative arrows. They actually do work. Next, we look at a matrix that cannot be diagonalized. Because apparently one successful example is all the universe allows before disappointment returns.